Hello everyone, I'm Pranav Nagarajan. I'm a fourth-year graduate student at Caltech working with Kareem, and today I'm going to be speaking about a spectroscopic search for dormant black holes in low-metallicity binaries. Why low-metallicity binaries? Well, to understand that, let's talk about the discovery of Gaia Black Hole 3 in pre-release Gaia DR4 astrometry. Gaia Black Hole 3 hosts a 0.8 solar mass red giant orbiting a 33 solar mass black hole in a wide, moderately eccentric 11-year orbit. And this discovery is already tantalizing for a couple of reasons. First of all, this is the most massive stellar mass black hole known in our galaxy, and also this is in the mass range of those merging black holes discovered by gravitational waves at extragalactic distances. But perhaps even more interesting is that the red giant is quite low metallicity of just -2.2. And if we look at all of the red giants in our solar neighborhood and look at their metallicity distribution, we see that only 1 in 10,000 of these red giants is as metal poor or more metal poor than the red giant in Gaia Black Hole 3, which implies that luminous companions to Gaia black holes are actually overrepresented at low metallicities. Furthermore, the red giant is pretty bright, has a G-band magnitude of 11.2, which seems to suggest that there might be many similar but fainter systems that are still waiting to be discovered. So just to again emphasize the motivation for our search and why we look at low metallicity binaries, let's talk about jelly beans. So basically, I have this jar of jelly beans here that represents all of the Gaia black holes. Of course, we don't see this jar, but maybe based on what we know about jelly beans, we think that the majority of jelly beans, all but one of them are orange, and there's only one blue low metallicity jelly bean. And then Gaia comes to us and draws 3 jelly beans from this jar, and we see Gaia Black Hole 3 as one of them, and then one of them is blue. And if you see this, you might be quite puzzled. How did we get so lucky? And so what you would do is you would reject what you initially thought about the jar, and instead, you might think that the jar has many more blue jelly beans. And in fact, it might be prudent, if you want to find Gaia black holes, to focus on these blue jelly beans. So what's our plan? Well, we went to this data-driven catalog of Andre et al. 2023, and we identified low metallicity stars that have large astrometric excess noise or Roue values in DR3. We were able to obtain spectra for over 500 targets using either the FAROS or APF spectrographs. Of course, we don't have the resources to solve the orbit of every single one of these objects, but instead, just what we did was measure epoch RVs and compare them to the mean RVs for these targets that have already been published in DR3. We look for the targets to have large RV shifts, identify them as promising candidates for compact objects, and then pursue additional follow-up. So why do steps 3 and 4 actually work? Well, to figure that out, let's look at the RV curve of Gaia Black Hole 3, which I've shown here. And you can see from the purple shaded regions that the epoch RVs of Gaia Black Hole 3 are different from its mean RV in DR3 by over 20 kilometers per second over nearly 70% of its orbit. And if you relax that to being greater than 10 kilometers per second, that's true over nearly 85% of its orbit. So even if you just measured one epoch RV, you would have to get pretty unlucky in order to miss Gaia Black Hole 3-like systems. You may also ask, why a cut on Roue? Why does that work? Well, what you can do is simulate the Roue of typical black hole binaries as a function of orbital period, and you find that regardless of whether you have a dwarf companion or a giant companion, if you use a cut of Roue greater than 2.0, you are sensitive to these systems at orbital periods of 100 to around 5,000 days, which is exactly the typical period range for the Gaia black holes that we're discovering with astrometry. And if you're wondering, how did I even calculate this curve? Well, it's do that code Gaia mock that Kareem wrote that allows you to simulate Gaia astrometry. Go check it out. So our sample looks something like this. I've taken all of the targets that we followed up and put them on an extinction-corrected color magnitude diagram. As one might expect for low metallicity stars, which are bluer at fixed luminosity, we see that they lie leftward of the traditional main sequence. We also see that those targets are spread all over the sky, but the main takeaway I want to say here is that based on what we followed up, we essentially have a nearly complete sample of stars that have metallicities less than -1.5, Roue greater than 2, and G less than 15 in Gaia DR3. So then we can go ahead and start measuring RVs. So here I show a observed FARO spectrum for a typical target in our sample, and I've plotted over it the BOSC Kurut's template spectrum that has the stellar parameters closest to those that were estimated for the star by Andre 2023. You can shift your template relative to observed spectrum and see where the chi-squared statistic is minimized in order to measure an RV. And basically, with some trial and error, we found out that the most prominent signal in these spectra seemed to arise from the magnesium 1b triplet. But life is not always that easy. And you get some spectra where you can't easily measure one RV. For example, there are some spectra that show signatures of two luminous components. And these are your sp2 systems or your double-line spectroscopic binaries. Here's an example of one of them, and you see two local minima in your chi-square curve, and we flagged those and removed them from our table of candidates. There are also hot stars and fast rotators that don't have prominent absorption lines. And these are interesting on their own, but for our purposes, it makes it hard to measure robust RV, so we removed them from our sample. And then finally, you have some spectra that are just low SNR or have potential moonlight contamination, and we threw those out as well. So here are our main results. We see here we've plotted the mean DR3 RV for everything against our most discrepant epoch RV measured with either Pharos or APF. And you see that most of our epoch spectra, or epoch RVs, are in good agreement with those mean RVs in DR3. But there is quite a bit of scatter around that one-to-one relation, implying large RV shifts. And you see a lot of that scatter is driven by those flagged spectra, so they're just spurious. But there are a bunch of promising candidates. We see 67 of our targets have discrepancies greater than 10 kilometers per second, and 10 targets have discrepancies greater than 20 kilometers per second. Of those 10 targets, Gaia black hole 3 is one of them. And so our search does recover Gaia black hole 3, and it kind of stands out. But you can see that there are some targets that are even more promising, like this guy up here that has a discrepancy of more than 90 kilometers per second. And well, I'll talk about that candidate soon, but I just want to mention for a few of our objects, we do have multiple epoch RVs that we're able to measure, and they show some interesting behavior too. So let me show a couple of interesting typical examples here. On the left-hand panel, you see an object that has 3 epoch RVs. There's a discrepancy with the mean RV published by Gaia, and you can see there's some slow RV variation over time, but we don't have enough to solve the orbit quite just yet, and so further follow-up is necessary, and that's ongoing. In the right-hand panel, you see something interesting. You see short-term RV variability that you do not expect from the published Roué. So what's going on there? Well, essentially what's happening is that the high Roué is being driven by this outer tertiary, but the short-term RV variation is actually due to an inner binary. So what you're seeing here is something that's likely to be a hierarchical triple system. And we think that these hierarchical triples represent a primary contaminant of our sample because, of course, not everything is a black hole. Yeah, well, that's what Smedar would say, yes. Back to our promising black hole candidate. You see the discrepancy is really large, so we got a bunch of RVs of it over the time period in which we wrote this paper, and we see this slow acceleration of negative 11 kilometers per second per year. So how do we even explain this? Well, again, we don't have enough to solve the orbit just yet, but just to explain everything that we observe, assuming the DR3 mean RV is correct, you can only explain this with large companion masses, long orbital periods, and high eccentricities. We did, as you can see, there's one different colored point. That's a high signal-to-noise ratio mic follow-up spectrum that we were able to obtain. And we show a cutout of that spectrum here. First of all, you see there's nothing really anomalous about this target. It just looks like a typical low-metallicity dwarf. It doesn't have any anomalous abundances. There's nothing weird going on around H alpha. And we also are able to rule out a secondary that makes some significant contribution to the luminosity. So we don't see anything striking just from the Mike fault spectrum, and I think further attention to this target is warranted in the future. So, of course, as any good observer, we need to be able to understand our selection effects and our search sensitivity, so let's talk about that now. First of all, how many black holes do we even expect to be in our observed sample? To do that, first I need to generate a mock population of black hole luminous companion binaries in the Milky Way. So I just make some simple assumptions here. 10 solar mass black hole, draw star masses from a Krupa IMF, take some log uniform periods, thermal eccentricities, random binary orientations, and magnitudes that we draw from a missed isochrones and evolutionary tracks with low metallicity. We want to paint them onto the galaxy. We are looking here at probably stars from a halo distribution rather than disk-like stars. So we decided to draw galactocentric radii from a halo density profile. And then we take our observational cuts and apply them. So we have cuts of distance less than 2 kiloparsecs, G less than 15, Roué greater than 2.0, and this gives us a mock population to look at. Now, initially, if you have your mock population before the observational cuts, of course, from a Krupa IMF, you will think that there's going to be a lot more low metallicity dwarfs than giants. In fact, you have over 100 times more dwarfs than giants. But once you apply your cuts, that goes down. And what we see is that for every giant black hole system that we expect to be in our simulated sample, we expect 8 times as many dwarf black hole binaries. And so if Gaia black hole 3 is the only low metallicity giant black hole binary in our sample, then there's maybe up to like 8 times as many, or order of 10, dwarf black hole binaries in the sample. And so how many of them would we actually recover using our search strategy? So let's begin with our mock binary population again. And then for some given orbital period and black hole mass, you can take some random orbital phase and then simulate one mock observation at a random time, one epoch. From that, you can calculate an observed epoch RV, and also you can calculate what DR3 would see as a mean RV. And then again, you apply your cuts. What fraction of those binaries have RV discrepancy greater than 10 kilometers per second, and also calculate a Drew weight greater than 2.0. And you get curves that look like these as a function of orbital period. And there's quite a bit to take in here. It seems to peak at orbital periods of few to several hundred days. But what we find is that assuming typical orbital periods around 10 to the 3 days, and also typical black hole masses, we expect our search strategy to recover about half of the black holes in our sample. So half of that order of 10. Okay, I'll throw up my conclusion slide here. And essentially, I just want to comment that we still need to constrain the companion masses. Follow-up of targets is still going on. As you see, we didn't observe 100% of the targets. And further spectroscopic follow-up at maybe around the release of DR4, when we'll get epoch astrometry, will help us figure out how many unseen black holes and neutron stars actually are in this sample. And you can find the paper linked with that QR code. Thanks.
Thank you. Nice job. I have a question. Gaia BH3 is in a stream. Is there anything particular or interesting about the environment of those candidates that you have? And did you consider doing your selection effect a little bit differently, thinking that there will be some population in streams that may affect your underlying sample?
I did not consider like the effect of streams. We intentionally made cuts on tangential velocity and things in order to remove contaminants that might be higher metallicity from like a disk component. So we think that a lot of the stars are from the halo component of the galaxy, and we do indeed see that Gaia Black Hole 3 is on this like halo-like orbit. But yeah, I didn't consider the effect of streams specifically.
And none of these candidates are in a specific location? Do they have like a unique environment, like a stream or something else, non-stream?
I didn't look at specific targets to check their environments, but you can see that they're just distributed all over the sky in LB coordinates.
Thanks. So in your thinking about your jars with beans, do you think that the fact that, the starting assumption that there are few blue beans and then you revise this to have more of them is only because, the incidence of massive black holes is higher at lower metallicity, or perhaps the starting assumptions that there are few low metallicity stars in your sample is also wrong? Yeah. So are you confident in the metallicity distribution that you started with, or is there room there for missing stars?
Yeah, so I think the initial assumption that I was making there, just by looking at all stars regardless of whether they have a black hole companion or not, but you're right that from theoretical considerations, there may also already be reasons to suspect that companions to black holes might have low metallicity. For example, low metallicity stars might remain more compact in their evolution, and this might make it easier to have a black hole companion. And so that was just to show, if you thought that, like I showed the metallicity distribution of giants in the solar neighborhood, if you started from that kind of assumption and you just were a pure observer who saw Gaia Black Hole 3, you might have already reason to suspect, just based on that if you have a black hole companion, the star you observe as a companion might be having lower metallicity than you might think.
Okay. Can I just...
Yeah.
Ask if there is a particular reason you picked this metallicity cut of -1.5, or is this more or less arbitrary?
I think there's some degree of arbitrariness there. I mean, you just want to pick some number that restricts you to low metallicity stars, but at the same time, you don't want your sample to be too huge that you can't follow it up.
Actually, my question follows on this. Gaia BH3 is not only a blue jelly bean, it's a dark blue jelly bean, right? It's very, very metal poor. And so I presume you didn't pick minus 2 point something as a cut because there aren't enough other stars around, right? It's one of the... do you think that exercise can be turned into, let's presume we're out of luck and find nothing there, can that actually be turned into a quantitative statement that there must be a metallicity dependence in the incidence even with the statistics of one object?
So if we don't actually end up finding anything there,
That's
sure,
right.
yes.
That
sure.
you've looked at it, many slightly less metal poor ones find nothing. Does that not add evidence that very metal poor is a good place to make a big black hole?
Yeah, I think definitely if we continue this and we find nothing, then that means that one of the assumptions I made when I was trying to model how many black holes there would be is not correct. And you can obviously build some kind of probabilistic model and then place some constraint on what you expect. I think that's definitely true.
All right, let's thank Pranav again.
Okay.